Good morning, and welcome to Saturday Minute Morning Physics for everyone. Today it is my pleasure to introduce our speaker, Professor Peter Abbamonte. Professor Abbamonte got his PhD actually from here, though he tells me the research was actually done at Bell Labs, although his diploma says University of Illinois. He then had postdocs in the Netherlands, at Cornell, before he was staff at Brookhaven National Lab, and then we managed to lure him here to Urbana-Champaign, where he is now a professor of physics. Professor Abbamonte has numerous accolades. He is a fellow of the American Physical Society, as well as a Moore investigator, and today he's going to tell us about how laws, sausages, and science are made. Right. Thank you.
Oh, I turned on the mute. They put two of these on me. Hello. Aha. So, good morning. Thanks, everybody, for coming out. This is the first one of these I've done, and Inga invited me to participate in this wonderful event. And I accepted because she told me that I could talk about anything I want. And I think the expectation was that I would talk about condensed matter physics and materials, but I decided not to do that. I'm going to talk about sort of a meta topic. And the reason I'm going to do this is because I've always had a bee in my bonnet about the meta issue of the public perception of how science actually happens. Because I think that a lot of the public believes that science occurs in a very rational and methodical and procedural way, sort of like building a building or a bridge. And in fact, it's an extremely nonlinear, in my opinion, very creatively motivated topic and subject matter. And the fact that it is not like building a building is very intimately tied to the fact that people don't learn that well out of books, and the fact that life doesn't unfold in a totally procedurally way. They're very closely related things. So for those of you who are old enough to catch the reference about sausages, there's this famous statement that actually, if you go back far enough, was attributed to Otto von Bismarck, who was the first chancellor of Germany. And there are various translations from the German, but my favorite one is, "To retain respect for sausages and laws, one must not watch them in the making." Because so we've all seen the way Congress functions, right? And it is not a rational process either. In fact, it seems to get worse every year. And of course, nobody wants to know what goes into sausages, especially those of us who've read Upton Sinclair. So the thing I'm going to try to convince you is that science sort of fits in this same category sometimes. I mean, sometimes it works out to be procedural. And when it does, we're all incredibly happy. But it doesn't always work like that. So let me start out with a question. How many of you have heard of the scientific method? I learned this in the 8th grade, okay? And the way I was taught it, which is what's on Wikipedia, is the following. So this is attributed to, many scholars were the origin of this, but it's usually attributed to Roger Bacon and William of Occam's razor, if any of you have heard of that. And it goes like the following. So this is the procedure of science. So if you want to do science, you follow this procedure. So you start by asking a question. So you have some knowledge of the world that's incomplete. You want to make it more complete, so you ask a question based on your knowledge. And then you want to get an answer to that question. So how do you do it? Well, first thing you do is you guess an answer. So you formulate a hypothesis. You say, the answer to my question is X. And then based on that hypothesis, you make a prediction that tests that hypothesis. And then you do some research. You get some federal grant money and you spend it, hire some graduate students, hire some postdocs, spend the money, and then you find out if that hypothesis was true. And if it turns out it's false, you reject the hypothesis and then create a new answer and iterate spending money in this money spending loop until you get to a prediction that was right, and then you accept it, and then you have the answer. And then based on that answer, it goes into the overall knowledge base that allows you to formulate a new question. And then you build science brick by brick until we understand the world. You already have a question. Yes, sir?
What is the problem with publishing things that don't work?
Ooh, that's a good question. Can I say that till the end? Because I could actually give a whole talk on just that. Oh, the question was, what's the problem with publishing things that don't work? And actually, I'm going to argue that even the things that don't work worked, as long as you learned that they didn't work. Then you have a statement to make. Okay, so there is no problem with it, though it takes some skill in crafting the manuscript. Okay? Okay, so here's the thing. So this is the scientific method. My kids have learned this in school as well. And the thing that I would like to say, which probably won't surprise you by this point, is that I hate the scientific method. And the reason is because that is not what happens. And let me just do a little foreshadowing. The scientific method is based on the assumption that all of your assumptions are true. Okay? So I'll give you a quick example. Let's suppose I believed that the world was flat. I could then formulate, based on my knowledge, what is the shape of the world? Right? It's a flat thing. Is it square? Or is it round? Or is it triangular? I could actually measure that, and I could formulate a hypothesis. The Earth is square, meaning a square, flat thing, right? And then I could test it by saying, okay, I'm going to sail to the edge of the Earth, and I'm going to measure its shape, and then I will find out what its shape is. The problem is, when you set out to sail, you find you don't get to an edge. All right? So now there's no accepting or rejecting your hypothesis because it was based on false assumptions that were wrong. Okay, and then that's what happens most of the time. And then what you have to do then is be ready to improvise. And okay, now I have to start thinking about what's new questions. Okay, and often the question doesn't come until you've got the answer. But I'm getting ahead of myself. So, well, the point I'm going to try to make this morning is that this whole thing is completely ridiculous. And what I'm going to do is I'm actually just going to give you a personal example of my own experience in this. I'm just going to tell you a story from my own life, which maybe is revealing too much personal life to people I don't know. But I'm just going to tell you a story of how this has unfolded in my own career and what we do in science when this kind of thing happens. Okay? So to do this, I'm going to rewind to the year 2001. When I was a scientist, we were actually living in Europe. My wife and I, we had a little baby. We had another one on the way. And I was working at that time. We were on an international fellowship. We were working in Europe, in the Netherlands, which in Groningen, which is a city that looks like that. It was very beautiful, great adventure. And I was actually working at a university there, and we were working on a new kind of technique that was in development at that time, which was called inelastic X-ray scattering. So this was a new generation of techniques that are done at accelerator facilities. So many of you may know that in the old days, we built many particle accelerators that look like this. And the reason was to do colliding beam physics, and then you could study the fundamental constituents of matter, quarks and gluons and so on. There's a new generation of facilities like this where people don't actually study fundamental particles anymore. They use these things like light bulbs, and they study materials. So these are used to measure protein structures. They're used to measure tensile strength in trash bags. They're used to measure electronic processes in superconductors and magnetic materials. So there's much more eye-level stuff going on at these kinds of facilities now than it used to be in the old days. By the way, does anybody know which one this is? Anybody seen this before? Yeah, that's in Chicago, by the way. Cost $1 billion. How many people have heard of Chicago? Oh, good. Well, anyway, so you should know about it. It's there. And it's an amazing facility. So anyway, there had been this technique called inelastic X-ray scattering. By the way, in this talk, I'm going to give a lot of technical terms. And I don't have time to explain them all, but I hope the storyline kind of makes sense. So I'll do my best to explain everything. But there's sort of the meta. I want you to pay attention to the meta issue of how do things work. Okay, so we had this technique called inelastic X-ray scattering. We'd been working in Europe. There's another accelerator like this one in Grenoble that is similar, where we'd been trying it out. And the bottom line is it just didn't work. I mean, something like $50 million had been spent worldwide on this, developing this technique to study superconductivity. And a lot of demonstration experiments were done that showed that it just simply didn't work for that purpose. So now what do you do? This doesn't show up in the scientific method anywhere. I spent a whole lot of money on something and it doesn't work, okay? The scientific method doesn't tell you what to do about that, all right? So I actually came back. We were actually visitors at Brookhaven National Lab for a short time. And I went up, I gave a talk at Cornell where I had some friends. And I gave a talk on this technique. And I said, look, superconductivity doesn't work. And that was my talk. So that's actually a good, similar question. And in a seminar, you can kind of say anything and it's okay. And one of the things that came up was maybe we could actually use this thing to do biology. So let me get to that, back to that in just a second. Okay, so the way the technique works is you take a photon, an X-ray photon, which is a particle of light from one of these synchrotrons. You fire it at a material. This is a cartoon of someone's cartoon of what a superconductor looks like. And then the thing scatters, and by measuring the angular dependence of the scattering, you can back out what's happening to the electrons in the superconductor to tell why the thing is superconducting. Okay, that was the original idea. It turns out that it never really worked because you didn't get enough signal. But I went to Cornell and I met with a couple of biophysics people, and we got talking, and we discovered that maybe this thing actually had applications in biology. Okay? And the application we came up with was actually in photosynthesis. How many people have heard of photosynthesis? Okay, good. I mean, life on Earth exists because of photosynthesis, so that's way more important than superconductivity. I hate to say that because I still study superconductivity. So just to be more specific, there are these bacteria that are called purple bacteria. So this one is called Rhodobacter spheroides. This is a little bug. It's about 1 micron or 1,000th of a millimeter in size. And on the outside of this thing, it has 2 membranes. And what this thing can do is these things can eat sunlight. Okay, you shine light on it and it generates, well, not food, but energy. And the way it works, it's really, it's absolute, as a physicist, when I learned about this thing, I couldn't believe it. It's the most amazing thing. So it's got a hard husk on the outside. It's got one membrane that protects it from the environment. Inside that is another membrane called the plasma membrane. And inside that plasma membrane is this machine that generates energy. And it's really extraordinary. So what it is there's a thing called a reaction center, which if you can excite this thing with light, it can actually do some chemistry that generates a thing called hydroquinone. I'll get to that in a second. And if you can funnel energy to this thing, then it can actually do some chemistry that generates energy. So the problem is it's very small, and so there's a question of how do I get the sunlight to shine on such a tiny thing. So what has happened is nature has evolved what is basically an antenna complex. So if you look around this reaction center, it has a whole bunch of rings of chlorophylls, okay, and other pigments called carotenoids. And what happens is when light hits one of these things, it generates a little pulse of energy called an exciton. And I won't get into what excitons are. But the excitons then gather the sunlight, and they propagate the energy down to this reaction center. And that allows the thing to gather a whole lot of sunlight and funnel it all to one place to do some chemistry. Okay? So what it ends up doing is it creates this hydroquinone thing that goes to a thing called a cytochrome C, which is like a pump for protons. Okay? So there's a membrane here, and this thing pumps protons across the membrane, and you get a voltage. I mean, really, it's like 20 millivolts. You could measure it with a voltmeter. And then that voltage is used by another thing called ATP synthase, which is like a giant lollipop, giant meaning like 100 nanometers or something, 50 nanometers, sticking through a membrane. And then when the protons flow back through, this thing turns like a machine, and it generates ATP, which is the energy of all your biological processes. It's incredible, the molecular machine, unbelievable. Anyway, at that time, so getting back to this X-ray scattering technique, there was a controversy in the literature, and it was actually started by Klaus Scholten here, and who's a faculty member in physics. And the controversy was, how do these excitons get this energy down here? So they're little, let's just call them little bursts of energy. So there's a question whether the excitons propagate and travel down here coherently, or do they de-excite and hand the energy to another exciton and sort of do a handoff and send the energy that way? And this was actually quite a big controversy in photosynthesis at sort of the turn of the 21st century. Okay? So what we discovered while I was visiting Cornell was that you could actually potentially answer this with this X-ray scattering technique. Now, we developed it for superconductivity, but it ought to be able to answer this question too. So basically, so I don't want to get too much in the details, but if you measure the absorption of this stuff just using visible light, it has certain absorption bands that correspond to these excitons. And it turns out if you if you excite those absorption bands with the X-rays and measure the angle dependence of the scattering from them, you can back transform out how far the excitons propagate. Okay? So it would take me 2 hours to give you all the physics for why that happens. But let me just say that if you can see these things in an inelastic scattering experiment, measure their angle dependence, you can answer this question. It's a rather well-posed question in biology and had some pretty big implications for understanding of photosynthesis. So then I had to make sort of a career decision. I mean, we had a new baby. Actually, the baby was just born. Both of these kids are at Urbana High School now, by the way. None of them are here, of course. They're all doing other stuff. And so I had to make a decision. So if this worked, it could be a really big deal for my career, right? Because, you know, in science, the way you get a job is you get great results. And then people say, oh, this person knows how to get results, and then they hire you, okay? So your existence hinges on productivity. And if you have a big hit, then your life is good. You get more money and job security and happiness and all that stuff, and your wife stays married to you and that kind of stuff. And your kids, you know, want an iPhone when they're 15, but and if you don't, then you have a big problem. Okay, so it's a gamble. So science, there's a gamble that happens, right? If you start a company, you're gambling. If you get married, you're gambling, right? You're making a bet on something that's big. But you have to make a decision. But you can't do nothing. So to make a long story short, we decided to do it, okay? And so I took a job. I convinced my wife that this was the right thing to do. I took a job at Cornell. So the guys there invited me out there for a postdoc or sort of a visiting scientist kind of position. And they said, come here for 2 years. We have money for 2 years. Let's try it. If it works, we'll all be rich. Well, rich in the scientific sense of credibility and security and funding and stuff like that. So this was sort of the scientific method question, if such as it is, was can we use this technique to measure the propagation characteristic of excitons in LHC? LHC is the name of that antenna, light harvesting complex. Okay? So we moved to Ithaca, pulled up stakes, bought a Saturn station wagon, which was the biggest mistake I ever made. There were many more mistakes in store. Actually, my first day of work was 9/11. I mean, there were so many Friday the 13th level omens coming. I mean, there was the Saturn, there was the 9/11 was I was at my benefits meeting learning about health insurance, and they said, oh, by the way, the World Trade Center just went down, okay? So that was just to put it in historical context. Anyway, that's a separate discussion. So the boss was Saul Gruner, and he hired me. And the thing about, so I went out to Cornell. So the thing about Cornell is at that time, actually still has one, it has an old accelerator underneath the soccer fields. It's called Caesar. Okay, we actually used to have one here, but we shut it down. They still keep theirs going. And a lot of the big facilities, like the one in Chicago and the one in Grenoble, were much more capable. But this thing about this one is it was small, and it wasn't as rich and it wasn't as visible, but that gave you a lot of flexibility to try new things. So it was a good place to go and just try something different. Okay? So at an accelerator, you can't just walk in the door and use it. You have to collaborate with the staff who run the facility. And I had a friend named Ken, who I worked with for many years, who also was a staff member at this accelerator. So I went to Ken. I said, Ken, what do you think of trying this experiment? He says, awesome, let's try it. Always wanted to do some biology, okay? And the other thing is there was also a guy at Cornell named Jim Shapley, who I believe is a student here. And he was a bacteriologist who grew rhodobacter. So it was kind of all the right stuff at the right place. So I went to Jim and I said, hey, can I grow some rhodobacter in your lab and try to isolate these proteins? He said, okay, let's try it. So we did. All right, so a very important part of science is it isn't all just going from one box to the other. If you want to get something done, you have to build a consensus, right? You have to get a team of people together to tackle a problem. It's not that different from doing anything else. Okay, so we had 2 years, 24 months. You get a result, your life is good. If you don't, you're sunk. So what does sunk mean? Sunk means Sal had 2 years of salary for me. At the end, it's not clear where I work, and I had 2 kids now. I just had a baby. Okay? Ken runs a beamline at this synchrotron. He's on a funding cycle too. He has to show productivity for his beamline. If it doesn't produce, they shut it down. All right? If it does, they give him more. It gets to expand. So he's got skin in the game as well. All right? Sal is a little isolated. He's a senior guy. But if we mess up, he looks like an idiot, which isn't great either. Okay? So there's a lot of things at stake. Okay, so 2 years. Got to get a result. 24 months. The first 6 months were simply done in preparation. Okay, so if you dig under the ground and look at what's at this storage ring, there used to be an old nuclear physics detector. That thing is shut down now. But there are a bunch of little experimental stations, and we had to find one that was suitable for this kind of experiment. The one we picked was called C1, this little box right here. Okay? So the first 6 months simply was modifying and upgrading the front-end optics of that beamline to make it feasible to do this kind of experiment. All right? That took 6 months. In parallel, I worked with this guy, Jim Shapley, to learn how to grow these bacteria, Rhodobacter. Okay? And you can't just grow them. You also have to extract the protein from the membranes. And that's done with, we use some old school technique called sucrose gradient techniques, which are, I'm told, are never used anymore, but it worked great for this. So I had to learn that. So this whole process took 6 months. Okay, so that's 25% of the time off the top. Boom. All right? So, but okay, after 6 months, we had the optics. The spectrometer was working. We had some dilute solutions of the protein, so all that had to be done was put the protein in the beam, measure a spectrum, see if we can see those exciton lines like in the plot that I showed you. So guess what happens? It doesn't work. I mean, nothing ever just works, right? That's the principle of, what is it, Murphy's Law, right? Murphy's Law is implemented in science every day. The only time something works is when you've eliminated all possible things that can go wrong. And there's nothing left but for it to work, okay? So you put it in, you try it, nothing ever works the first time, so it doesn't work. So I won't get into what this axis is, but it's something like energy. There's a big peak that's elastic scattering. What we were looking for were these exciton lines, and you don't see them. So why don't you see them? Well, 2 reasons. The first thing is, well, one is they're just not, the scattering isn't strong enough. So you need to, you know, the strong amount of scattering really has to do with how much protein you can pack into the beam. And it was a pretty dilute solution, so we didn't really expect to have a lot of scattering the first time. And, but one thing that went wrong is there was quite a bit of background, and we didn't expect this background to be there, didn't even know what it was from. So that was a little bit unnerving because now, you know, if you don't have any background, you can detect things even if they're very faint. But if you've got a background, its intensity better be bigger than the background or you can't see it at all. Okay, so now suddenly the issue becomes we have to concentrate this protein, right? So I had a dilute solution. We need to pack more protein into that solution to amplify the signal of that over all the background and stuff. Okay? So that's what we did. So we spent 2 months using ultracentrifuge techniques to take this dilute protein and sedimenting it into a really highly concentrated purple gel. Okay? And these gels were really beautiful. They were these purple droplets of stuff. I wish I had pictures of them. My cell phone didn't have a camera in those days. That was 5 years later. But yeah, anyway, so we tried that. So then we said, okay, this is really concentrated now. We put it in the beam. Maybe we'll see some exciton lines. So guess what happens? Nothing. That little blip. Okay, this is, by the way, photocopied right out of the lab notebook. Okay, so that circled thing with an arrow was wishful thinking that that was a peak, but that's just noise. Okay, so now we start getting pretty nervous. We thought, uh-oh, we've actually put a concentrated solution in, and we can't, and we still don't see it. And there's this weird, what the heck is that? There's tons of signal in this thing. We had no idea, had no expectation it would happen. Then we thought, all right, it's time for one last stab at this. I mean, this took 3 more months, right? So we took one last stab at it. We said, all right, now we're going to, so let's forget about gel. Let's take away all the water. We'll take one of these gels, totally dehydrate it into a solid block of protein. Okay, 100% protein. It can't possibly be too weak still, right? Because there's nothing there but what we're scattering, what we want to know, right? Any guess what happened? Yeah, nothing. Uncensored right from the lab book on the beamline. So still can't see them. Okay, now you should be nervous. At least I was. Why? Two babies. One of them is now 14 months older, walking. Okay? And no excitons. And now it's clear the experiment not only didn't work, but it can't. It won't work, ever. Because you can't possibly concentrate something further than a solid thing. So that means this background is going to win no matter what. So the whole thing failed. And we're 14 months into a 2-year project, and Ken had a grant review coming up to assess the funding of his beamline, and should it be continued. And he could have been doing other stuff all this time, right? That would have been very safe and would have got him some papers out. He would have got renewed, and he didn't. He did this instead. And he was pissed at me for convincing him to do this, which is totally unreasonable, because if I tell you go buy stock in Apple and you do it and it goes down, is that my fault? It's your fault for listening to me, right? Anyway, it doesn't matter. Here we are in this situation. So what would you do? All right, so here's the question. What would you do in this situation? Oh, yes. All the grown-ups, all the over 40 people, I go look at that background, right? The people who know the scientific method doesn't work, right? Right? Because they've been around long enough to know. Yeah, I go, so we went and looked at that background. What else can you do? I don't know. So the scientific method is gone, right? There's no question. There's no answer. You're just lost. And all you got is something, and you're just going to look. So we just started studying that. And if you look at it closely, it's a peak, okay? That thing was not a background. That was an excitation. It wasn't the excitation we were looking for. It wasn't the exciton that we wanted. It was a different excitation. So I had to go in the library and do some homework to figure out what this thing was. But it turns out what it is an object called, oh yeah, one last thing. So we saw this in the protein. At one point, we just pulled the protein out. We put a capillary of liquid water in there, and we saw it in just plain liquid water. So it had nothing to do with the protein at all. Okay, so at that point, we were just studying a weird peak in water. All right? So if you ask, what is this thing? The answer is, it's an excitation called a plasmon. Anybody heard of a plasmon? Okay, no. So what's a plasmon? So you know, if I have a lake of water, I drop a pebble in it, it will excite a surface wave. The surface wave will propagate along it. What a plasmon is an excitation like that in the electrons rather than in the density of molecules. Okay? The difference between a plasmon and a water, like a surface wave, is the time scale. Plasmons oscillate on time scales of attoseconds. I'll talk about what an attosecond is in a minute. Okay? So it's an electronic object, and it's wicked fast. Okay? So we saw this plasmon. We're sitting there studying water. We have no idea what to do with it. And we're having a conversation one night, and I said, well, you know, if the exciton experiment had worked and we actually had gotten data from the light harvesting complex, the plan at that point was to use the momentum, the angle dependence, to reconstruct how the thing propagates. And that would have been developing some new algorithms for analyzing scattering data. And I said, well, maybe we ought to just do that on this instead. I mean, I don't know what else to do. And that was something that I was interested in trying, so maybe we should just do it on this thing instead. And then I don't know what's going to happen, but let's just see what happens. So just in case there are any card-carrying nerds in the audience, all right, I shouldn't do this, but it turns out that the thing you actually measure in these kinds of scattering experiments is called a Green's function. Anybody heard of Green's functions? Wow. Okay, we've got some really hardcore people in here. All right, a Green's function is basically the response of a system due to a point disturbance. Okay, so if you take a pebble and you drop it in a pond, the ripple forms as a function. That's the Green's function for the surface waves. This basically was measuring the Green's function for the electrons. So I thought, so it looked like, okay, maybe we could take the scattering data and actually reconstruct this Green's function and see what it looks like for this plasmon in water. I don't know what we learned. So I definitely won't do this slide, but that took about 4 months of mathematics and learning about algorithm development and stuff. And when we were done, we actually had some movies of the plasmon. And here's what it looked like. So that's, for the purists in the audience, the Green's function for the plasmon in liquid water. You can see it sort of looks like the response of the system to a point disturbance. Sort of like hitting a drum. You know, you excite some waves, and then eventually it sort of damps out. And I went and I showed this to Saul, because he was my boss. And I said, well, I have these movies. The protein experiment didn't work, but I have these movies. And he said, what's the time scale? What's the frame-to-frame time of these movies? And I said, well, it's 4 attoseconds. Anybody know what an attosecond is? What's an attosecond? Actually, I wrote it here. Sorry, I just finished my talk this morning. It's 10 to the minus 18 seconds. Okay, so anybody know how old the universe is in seconds? It's about 10 to the 18 seconds old. So an attosecond is to a second as a second is to the age of the universe. Right? And the time scale of this thing is attoseconds. So this movie is really fast. I mean, insanely fast, right? And it's movies. This is 10 angstroms full scale, right? It's 1 nanometer, okay? So, I mean, and if you look closely, there's tons of physics in this. So if you divide it up frame by frame, then, you know, at t equals 0, the lake is sort of placid. When you hit it, you get the drum head goes down with the disturbance that goes up, and it propagates and distorts, and eventually it turns into heat. So actually, this was actually the first time that anybody had, you know, what's hidden in this, by the way, is the second law of thermodynamics, okay? If you create a low entropy state, as time goes on, it evolves and becomes more disordered and turns into heat, because the algorithms that we use turned out to use, all right, that's the Kramers-Kronig relations, which have fundamental things about causality in them and the second law and stuff like that. So there was some really deep physics in this. Nothing to do with biology, all, 0, okay? No photosynthesis anywhere. Anyway, I showed this to my boss, Saul, and it's, you know, the frame-to-frame time was a few attoseconds. And he said, you're doing attoscience. I said, what? What is attoscience? I said, go to Nature, type attoscience in, and hit search in the search bar and hit enter. So I did that, and turns out there was a whole research effort in chemistry, huge, in attoscience, because chemists are very interested in the electronic processes that drive chemical reactions. And this was a huge effort in chemistry. Big world global effort in trying to build lasers to do experiments faster and faster. The highest speed things they'd ever measured was sort of 800 attoseconds, not like just a little bit faster than a femtosecond. We had movies with 4 attosecond frame-to-frame steps, okay? So we wrote a paper. It came out in PhysRev Letters. And oh, by the way, I should tell you this. So in this movie, the thing I just showed you, let me show it again. I don't want to spend too much time on this. So this is the movie. So there's a start, and the thing evolves, and then after you wait a while, doesn't do a whole lot, it eventually evolves into heat. The entire time of that elapsed time is 350 attoseconds. That's the time it takes light to travel 100 nanometers in vacuum. Okay? Just to give you an idea of how fast the thing is. So we wrote a paper saying movies of electrons with attosecond time resolution. And the day it came out, reporters started calling on the phone. The first person was a science writer for Physical Review Focus, which at the time was the journal that highlights the most important science and physics every issue. And when that came out, Chemical and Engineering News is the lead public magazine in chemistry. And I had journalists calling me on the phone from Chemical and Engineering News. We ended up with the lead story in Chemical and Engineering News. was a huge deal. I started getting invited talks all over the planet at ultra-fast science meetings. I've never even heard of these people, right? I was getting invitations. I was traveling to Europe and Japan, giving talks on stuff that I'd like reading like crazy to learn what it is, right? So I don't sound like a complete moron at the meetings. But then, yeah, so suddenly we had the fastest movies ever made, okay? And so what happened after that is a long story, but the bottom line is, and still in my group we have a little program on ultra-fast imaging. So we've now made movies of, this is actually an exciton, not in a protein, but just plain old salt. Well, lithium fluoride, which is a type of salt. So we actually ended up getting the exciton experiment to work, but in something else. So that's what an exciton looks like. And this is a movie of electron dynamics in graphene. So that came out a few years ago. And it's been a pretty interesting program. And having discussions with ultra-fast laser people about the relationship between this way of studying dynamics and laser ways of studying dynamics has been enlightening for the whole field. We've all learned a lot about just understanding the relationship between these two ways of doing things. So what's the point of this story? Other than I'm still standing. The point is that the way we teach children how science works is the following. We tell them, you ask a question, then you do the research, spend the money, hire the people, right? Burn tax money, whatever, and then you get the answer. And then you can ask a new question. That's how we tell them it works. The way it actually works is like this. You ask a question, maybe, or maybe you just want to try something weird. But you ask a question, and then you do the research. And as you do the research, things that you didn't expect to happen, right? Little branches of loose ends appear. There's background that you didn't see. You tried to sail to the edge of the earth. You ended up coming back to where you were. Okay? Stuff that you didn't expect to happen occurs. Because your knowledge of the universe is incomplete. You cannot simply expect a measurement to either validate or invalidate a hypothesis. When you go into a measurement, it's like going into the forest. You don't know what's there, right? You're not just going to get there and say, oh, is the tree that I thought there or not? You go in there, you see rocks, you see wolves, you see stuff that you didn't even know about, right? And as you're going along, there are loose ends that appear, and you don't know where they go. And there's always more than one. And then as you go far enough, what happens more often than not is there ain't no answer. You hit a dead end. Earth isn't square or round or triangular. It's not even a flat thing, right? The excitons aren't even there. They don't scatter. There's something else, right? So why is there no answer? Because the question you asked was ill-posed, right? You thought that the world was a certain way, and it's not, right? So now this I call the deep, dark, murky state of cold reality. Now this is the point. All of you, whether you are scientists or not, will find yourself in this situation at some time in your lives. How many people have been in this situation? Right, everybody over about 30. Oh, right? High school kids are like, what? What are you talking about? All right? So this happens in science, and it happens in everything else. And so you don't know what the answer is. You don't even know what the question is. All you have is loose ends, right? So what can you do? You have no choice what to do. You have to just follow these loose ends, right? You just have to pick one and go. You don't know what's there, but you can just sit still. You could die, or you can try to find your way out, all right? There's a great Dr. Seuss book, Oh, the Places You'll Go. Yeah. That's what this is about. Okay? Anyway. What's that? Yeah, exactly. Exactly. You have no choice. There's two choices you choose, right? Okay, and then what you'll find is that many of these things are not interesting. They were just a red herring. It's a waste of time, okay? But then you have to keep going, right? You pick another one and you keep going. And then what you find is that at some point, there's an answer. So what do you do when you have an answer and you have no question? Well, but how do you publish? So this is a practical question. You make up a question that went with that answer. So if you read our paper, it says, there's great growing interest in attoscience techniques. We here have studied a new method for doing attoscience. And then you say that it happened like that. And then you tell a story. You lie. I mean, I hate this. You're not going to put this on YouTube.
It's creative edit.
It's, yes. I shouldn't have said that. You package it wisely. Anyway, you have to write a paper. Papers are written, here's the question, here's the methods, here's the answer. Yes, sir?
So are you saying that science is one big game of Jeopardy?
I wish it was that simple. Yeah, trying to guess the answer. Yeah, but it's a game of Jeopardy where they don't even tell you what the answer was. Right? You have to get that first, then the Jeopardy game can start. Anyway, so here's my scientific method. The first step of the scientific method is you try stuff. So you go off, so you can tell yourself you have a question, but all that does is tell you which woods to go into, all right? But you don't have to have a question. You just go off into the woods, okay? And then when you get there, you see that things happen that have never happened before. And then the next step is extremely important. The next step is to get confused, to not understand, and to accept that not understanding is okay. It doesn't have to be a procedure where you start with this and you formulate a hypothesis and then you test it. It's okay to just not understand, right? Because science is a learning process. It is not a bridge building process. So then you read the literature and try to understand what's going on, and then you try new stuff. And then, very important, you question your assumptions. I assumed that I would see exciton lines or the Earth is flat. Is it really? Right? And be open to accepting that your assumptions could have been wrong. And here's a very important one. Ignore the critics. Because the truth is, the general public and people in the government who fund science think that it works like the scientific method. And it's the cold truth. Okay? And and it doesn't. So the only way you can survive is to live in this world of ambiguity, but somehow package it so that it looks like the scientific method happened when it was done. Because if you tell people that the way it really happened, they will blame you for the fact that the world is confusing. Okay? And they won't blame it on them, they will say it's your fault. So you have to find a way to make it look like this very nonlinear creative process is not. Very, very important. So all of us who are faculty members running research groups, we all do this, right? So you're always telling a story as if it's unfolding like the scientific method while it's happening in a very nonlinear way. So every day you have a story to tell, and it changes day to day, right? And you make it sound like what happened in a logical way, even though it didn't. And that's the cold truth, and you have to do that. If you can't, you cannot be a scientist. It's a prerequisite skill. Anyway, so you ignore the critics. People will say, oh, you don't know what you're doing, and you don't. But you just keep going. So you don't give up. You follow your nose. You try to understand what's going on, and then eventually you get there. And then the final important step is very important. You lie, and you say that it happened like that. You write the paper, and you say, we formulated this hypothesis. And that's the way it works. And it's too bad, because I wish the world were like William of Ockham said it was. I wish that it were like a Disney movie, right? Where your dad's mean to you, so you go off and you you're a mermaid and you meet some cute guy and then you get on a boat and get married and it's all very simple, right? But it's not like that. So the conclusion is the scientific method is bunk. And the thing that is the most bunk about it is I think that it gives people from a very early age the incorrect assumption that science is a procedural thing. And there is a perception, so I talk to my kids in high school and they say, oh, you're a scientist, you're just a geek, right? And you're not creative. Creative people go into the movies, right? And it steers creative people away from a discipline that needs them, okay? So that's what's wrong with the way we teach it. Because it creates the false perception in the public for the way science works. You know, we have these climate change debates and debates about other things. And often it happens scientists don't agree with each other. And then you're like, well, how, if you guys can't even agree with each other, we have to make a political decision. I mean, how can we even rely on you? And they feel betrayed, right? But that's just the way it is, right? We don't know everything. I think climate change is settled, by the way. I'm not disputing that. But anyway, so there is a lot of bookkeeping in science. It's not just art. But there is a creative aspect to it. And exploring and being willing to understand and learn about the unknown is the most important part of it. Okay? And so my point is that not all creative people should become movie stars. There is room for you in other fields that may have more tangible benefits to society. I like movies too, but there's plenty of people who want to be movie stars. I encourage you to think about directing your creativity into other things too. And the key thing also is whether you choose to be a scientist or not, you will experience the unknown, and the way it unfolds is the same. So be ready. All right, so that's it. Thanks everybody for... Oh, when they ask? Yeah.
All right, well, that was an excellent talk, and we've got a lot of time for questions, so yeah.
Michael, yeah.
You subtracted the plasmon, I'm pretty sure.
What's that?
You subtracted the plasmon from the background. And what did you see?
Well, I didn't subtract it. I left it in there.
Yeah, I know. But
Michael's a physicist.
the original experiment.
Oh, the original one.
Are there excitons in?
Are you talking about the lithium fluoride one where we actually did it eventually, or the original one? We never saw the exciton, so we didn't subtract any. No. Oh, did I try subtracting it? Oh yeah, you bet. Are you kidding? I tried everything. No, there was the noise eclipsed the signal from the excitons. So you can subtract background all you want. You don't see anything but noise. No measurable excitons. Yeah. Do I know what went on with the photosynthesis? I never contributed to the topic, but eventually time-resolved laser people were able to establish that it was a handing off procedure and not a coherent delocalization. And actually the person advocating for the coherent delocalization viewpoint was Klaus Scholten here, and he was wrong. So in all respect to Klaus, it was an awesome idea, but too bad.
The model of the scientific method has its analog in mathematics research. People go all over the place. They finally get their ideas together. They write a neat proof, which has a beginning, goes its way through.
Yes.
And has nothing whatsoever to do with the way in which the discovery
Yes, exactly.
successfully hides it all.
Yep. And you write that was a statement, which was math works the same way. You fool around, you try to find something that makes sense. When it's done, you write it like a proof. That's what goes into the paper. But you didn't prove it like that, right? You figured it out. You started in the middle and you jumped around, and you probably ended up doing something you didn't even plan to prove, right?
But the report is supposed to be the result.
Yeah.
Not your journey
Yes.
in which you wandered for 40 years.
Yes.
I don't care about it.
You don't. Yep. So it's not. I'm not even saying this.
I don't think it should be written as.
It shouldn't. It shouldn't be. And if you did write a paper like that, it would be this long, and it would be this totally self-indulgent thing like this seminar, right? Yeah, so it would be a totally obnoxious thing to write such a thing. You're right. So I'm not saying we should change the system. I don't know what better system there is, but it's still, we live like this. There's some hypocrisy that is required, right? And it bugs me. Yes, sir.
2 points. One on your lie thing. Peter Medward wrote a nice paper many years ago making your point, not quite as deep as yours was, but the title of the paper is the scientific paper a fraud? And he basically said, hey, you know, it doesn't really capture what we really did.
Yep.
But we put it in this form, so it's an argument to make. But on kind of a deeper issue about your argument is the philosopher Peirce once argued that the stuff that scientists get taught by philosophers of science and other people is all wrong because it's either deduction or induction.
Yeah, exactly.
And he claimed there was the way scientists really work was something he labeled abduction.
Yeah, abduct, that's a good
And
word.
what he had in mind, what he basically says is that what abduction is you've got, it's like you said, you've got some phenomenon, and then you try to figure what the hell's going on.
Yep.
And you
Yep.
point it out and make it look like
So I think the point is I'm not the first person to say this. But I had to learn it. It's the hard knocks of life that I learned it with. So.
textbooks still, of course, if you
Textbooks still say the same old thing, yeah. Who's next? Somebody over here?
Somebody asked me a question about results that don't work out in other students.
Yes.
So the rest is, it couldn't hold.
Yeah, so actually so yes, he asked, how do you publish things that didn't work? The answer is nothing doesn't work. If you do a well-controlled measurement, you got a result. It's not the one that answers the question you asked, but if you shape a statement around that, you can publish it. So there's no such thing as a non-result. Up top.
Are you talking about how politicians make laws or laws that...
It's almost the same. Yeah.
Pardon?
I'm sorry, finish.
Are you talking about the laws that politicians make for us, or are you talking about laws of nature, laws of physics? What laws are we talking about?
In the original statement,
Yeah.
it was the laws that politicians make.
Oh,
Yeah.
okay.
Yeah, that was what, that's what is referred to in that quote, which was not mine. Yeah.
There was a Swedish scientist who won a Nobel Prize on superconductivity. He was asked to give a lecture on climate change. And he said, well, I really don't know much about it. But then he researched it, and he had the view that some scientists are not properly applying the scientific method to climate change. Now, ideally, you create your own planet and experiment and add carbon dioxide.
Yep.
So you can't do
Not
that.
so easy. Yep. Well, and also, let me be very clear on one thing. Even though science unfolds in a very nonlinear way compared to what people would like to think, there is still a very clear line between good science and unethical science. Because as you're going through this process, you can still falsify data. You can still truly lie, meaning say something that didn't happen did. Okay? So that's a very, very different thing. Okay?
But there's Gregor Mendel, the founder of genetics, who many people claim did fake his data, even though his theories were correct.
Yeah, so did Millikan's oil drop experiment, had falsified data too. And look, you know, let me tell you something else. The question of is scientific ethics, you run into gray areas where I have a student here, Mindy, right? Oh yeah, Ollie's here. We've sat down in the lab, maybe not with you yet, and said, okay, we have this result, and here's what we're writing a paper. Is this the ethical way to say it? Right? Because there have been cases of scientific misconduct where a person did nothing but process their data in a certain way and then didn't say it. Right? And if they had simply disclosed the way they had processed the data, it would have been considered good science. But by simply leaving out some steps, it becomes misconduct, right? Because now it's falsifying. So you walk this fuzzy line all the time. You have to make judgments every day on what's ethical and what's not. And it's not as easy as it sounds, which is not an excuse to lie, to truly lie and falsify things. But it becomes, you have to put energy and thought into doing things ethically, given how nonlinear and complicated things are. Yeah?
How should we teach science?
Oh, I was hoping no one would ask that. I mean, I'm a science teacher, and the answer is, I don't know. I mean, I've kind of gone cheap because I teach upper division physics majors and graduate students, and they're all already fairly experienced, and it's easier. How do you teach high school science? I don't know.
I'm sorry I missed the bulk of your lecture, but I came to the tail end and you talked about how you have to couch this stuff and quote in a way people understand it, but doesn't that leave you in the conundrum? Wouldn't you like people to know more that there is some uncertainty about science? Because
yes.
Sometimes some of your colleagues might come across as certain about things as other people that they claim to be and
yep.
So
yep.
how do you balance that?
It's very, very hard. And a lot of it has to do with where you publish. So if you write in an obscure journal where they'll let you write a nice long article, you can disclose more of what happened. When you're writing a short paper for Science or Nature or Physical Review letters, you can't do that. So I think it's about balance, you know, like if you've got a really sketchy study with a lot of nuance, you write a big long paper. If things are pretty cut and dried, you can write a paper in Science. In between, it's hard. There's just no universal answer. You have to look at every case by case and make a judgment, and it takes experience. And if you make a mistake, misconduct can happen. So, you worry about it every day. Yeah?
Yeah, I just wanted to mention that this process that you have up here also happens in industry.
Huh, you bet. Even more.
So it's not papers or publishing, it's actually
revenue.
Coming up with stuff.
Yeah.
And sometimes you're after one thing and you end up finding something else that makes a ton of money.
Yeah, by the way,
you didn't even know it.
Starting a startup company is almost exactly the same. Okay, very similar process. There was somebody up there with the question. Yeah.
I'm reminded of the Michelson-Morley experiment where they set out to prove the existence of something
yeah.
that actually proved the non-existence
yep.
because their experiments are well done.
Yep.
Did you learn anything that would be actually a positive result by not finding the exciton?
Yes. Well, let me tell you something. Michelson. So I've ripped a bit on the scientific method. There are cases where it gets used. All right. So if everything is well organized and a body of knowledge is close to the end, then often there's a scientific method type test at the end. And the Michelson-Morley experiment is a perfect example. People had speculated about a lot of different things in the ether, and there was a long discussion about that topic. And at the end, Michelson-Morley was able to actually do a test. But that was the end point of a long, messy dialogue that unfolded over decades, right? So I'm not sure what was your question.
I wonder if, in a parallel way, by not finding excitons, did you prove anything about excitons?
No. In this case, I just didn't see them. But you can publish negative results. So what I could do is publish an upper bound on the scattering strength of excitons in proteins, which 6 people in the world, including myself, might care about. And I actually never wrote that paper, but that's what you can do is put bounds on things. And we've done that. Yeah.
Suppose you wrote a proposal for funding from the government, for example, the Army Research Lab, and you wrote a very interesting question and the potential answers, for example, how to make an airplane.
Yeah.
But when you finish your work, you found a pair of questions and answers is quite completely different.
Yeah.
It could be how to make a sandwich.
Yes.
So how
exactly.
to write a report or...
You deserve a medal for asking that question. So how do you, so you want to get a government grant to do research, you have to propose a question, postulate some answers. What do you do when you wind up doing something totally different? I'll tell you what happens. You always write a grant proposal for the thing that's already done. Right? He's nodding. Everybody, this is what you do. So you go through this complicated process, and then once you've got it all figured out and you're working on the paper, but you haven't published it yet, boy, you're not putting this on YouTube. And I swear this is what everybody does. You write a proposal proposing to do the experiment that you already did, so that you can ask a well-defined question, which you didn't even know when you undertook it, and propose some well-defined outcomes, even though you already know which one it's going to be. And you put demonstration data in the proposal saying, we have shown preliminarily that this is going to work, so that they can't say it's impossible. And then you get the money and you write the paper, and it comes out, and while you're doing that, then you're trying the next thing. And this is the game you play. Okay? And that's the way it works.
One last question.
Yep.
So I was really impressed that when you went with your movie to your advisor, he was like, "Oh, did you think about these attosecond people, the attophysics?"
Yeah.
And you were like, "I don't know what that is."
I didn't even know what it was. Yeah.
And so I think my question is, how do you recognize people who are good mentors and who are connected to many, many ideas to help you connect to other ideas?
Oh boy. That's even harder than how do I teach high school physics? So the question was, how do you recognize good mentors? I don't know. You know, you go work with somebody and he seems cool, and then at the end you find out if he was good or not. So I just got lucky. I mean, I don't know.
How do you make yourself into a good mentor?
I also don't know. I actually don't know empirically if I am or not. You can ask my students after the meeting.
All right, well, let's give the panel speaker once again.